Assalamualaikum and greetings everyone. Today's topic is on line integrals. There are four sections on this topic. The first section is line integral of a scalar field. Second is line integral of a vector field. Third is conservative vector field. And the last section is on Green's theorem. Okay, now let's look at the first section, which is on line integral of a scalar field. Okay, so for line integral in a scalar field, we have two parts. One is for curve on a xy plane, and the other is curve in xyz space. Okay, now let's look at curve on a xy plane first. Okay, for a curve on a xy plane, you have many ways to represent your curve. One is you can represent your curve as y as a function of x, or you can represent your curve as x as a function of y, or you can represent your curve as a set of parametric equations where x is equal to f of t, y is equal to h of t. Okay, now let's look at the first bullet here, where your curve is given as y as a function of x. So line integral can give you the length of your arc, and also you can integrate a scalar field or a function over the curve. Okay, now let's concentrate on the first bullet here. Okay, now let's say you're given a curve on an xy plane, and your curve is represented as y as a function of x. So now let's say you want to find the length of your curve from point A to point B. So we want to find the length of the curve from point A to point B, from point A to point B. Okay, so what we're going to do is we're going to partition our curve into different line segments. Okay, different line segments. Let's say you partition it into a few line segments. Let's say 1, 2, 3, 4, 5 line segments. So here we have from point A to point B, we have one line segment, and another, here we have another line segment, and here we have another line segment, another line segment, and another line segment. Okay, from high school, we know how to find the length of a line on an xy plane by using Pythagoras theorem. Okay, now let's concentrate on one of the line segment. Let's say here. Okay, using Pythagoras theorem, I'm going to call this delta Si. Well, it's actually delta S1. And here this is delta X, and this length here is delta Y. Now, using Pythagoras theorem, we know that we can get the length of the line segment delta S by is equal to delta Y squared plus delta X squared, and then take the square root. Okay, so that would be the length of this line segment. Okay, now let's do some mathematical manipulation. Let's divide delta S with delta X on the left hand side. So we have to do the same thing on the right hand side. So we have delta Y squared plus delta X squared. We're going to divide with delta X as well, but if you put it inside the square root, then you have to divide with delta X squared and then the square root. Okay, now here you can simplify this as delta Y over delta X squared plus 1. Okay, because delta X squared over delta X squared is 1. Okay, now let's multiply both sides with delta X. So here we have square root of delta Y delta X squared plus 1 delta X. So that would be the length of one of the line segments. Now, if we want to know the curve, so the curve would be approximately equal to the sum of the length of the line segment. So if we sum up all the line segment, say I from 1 till, so here we have 1, 2, 3, 4, 5, 5 only. I'm going to call it n to make it in general. So this is equal to the line segment summation I from 1 till n. So here we have delta yi delta xi squared plus 1 delta xi. Okay, I from 1 till n. But if you want it to make, if you want this to be more accurate, what we're going to do is we're going to partition the line segments into more line segments. So the more line segments, the more accurate our answer would be. So we're going to partition that into more line segments, meaning that delta x and delta y will be very, very close to 0, very, very small. Then we have delta si, I from 1 till n, but here n approaches infinity because delta x and delta y will be very small, so we would have infinitely many line segments. So we do the same thing on the right hand side. I from 1 till n goes to infinity, and here we have delta yi over delta xi squared plus 1 delta xi. Okay, now from Riemann's summation, if we have summation I from 1 till n goes to infinity, then we can replace it with integration, Riemann sum. Okay, so delta will be replaced by ds. Okay, so here we have ds on the left hand side, and on the right hand side we have integration as well, because this bit here, the limit, the summation will be replaced by integration, and the delta y will be replaced by dy, delta x will be replaced by dx plus 1, and here we have dx. Okay, now x here, the limit for x, we're going to use the x coordinate for the starting point, so it's going to be x naught, and the upper limit for x here, we will use the x coordinate of the destination point, which is in this case xn. So this is the length of the curve from point A to point B, where your curve is given as y as a function of x. Okay, so that is ds. Okay, so length of the curve is represented by ds, but here ds, if your curve is given as y as a function of x, it's equal to square root of dy dx, sorry, that should be a squared, dy dx squared plus 1 dx. Okay, now back to our notes. So this is the arc length. Okay, s is equal to integration of ds, and here we have our integrand where I explained just now what ds is. Alright, but then if you have a scalar field, so let's say your scalar field is gxy, you want to integrate over curve C, then if your curve is given as y as a function of x, you replace this y here with f of x, and ds here is similar to the first item here, is equal to square root of dy dx squared plus 1 dx, and the limits is going to be x naught to xn, where x naught is the x coordinate of the starting point, point A, and the upper limit for x is going to be xn, which is the x coordinate of the destination point. Now for bullet number 2, it's the same process for item 2 here. If your curve is given as x as a function of y, same point A to B, the arc length is still ds, integrate over curve C, but then your integrand here, your ds is going to be dx over dy squared plus 1, and the integration is going to be with respect to y. The upper and the lower limits would be the y coordinate of the starting point and the y coordinate of the destination point, so y naught to yn. Right, so you have to change everything in terms of y. But if your curve is given as set of parametric equations, so then you have a parameter t here, x is given as f of t, y is given as h of t, then the arc length is still going to be ds integrate over curve C, but your ds now is square root of df dt squared plus dh dt squared integrate with respect to t, and the upper and lower limits would be the value of t at the starting point, t naught, and the value of t at the destination point, which is tn. And if you have a function or a scalar field, you want to integrate over curve C, then your x here will be replaced by the parametric equation for x, which is f of t, and y here will be replaced by the parametric equation of y, which is h of t, and ds is similar to the first term here, which is square root of df dt squared plus dh dt squared dt, and the upper and lower limits for t. Okay, here's a mistake there. That should be t naught. That should be tn. Okay, so you change everything in terms of t. That is for line integral on a xy plane. So you have three choices. Either change everything in terms of x, or change everything in terms of y, or change everything in terms of t, depending on how your curve is given. But if your curve is in xyz space, you have no choice. You have to change everything in terms of t, because for a curve on a xy plane, in the xyz space, the curve will be given as a vector valued function or as a parametric equation. So this is a curve given as a vector valued function. If it's given as a parametric equation, then your x is going to be f of t, y would be g of t, which is the parametric equation for y. Z is h of t, which is really the z component of your curve, rt there. Okay, so the arc length is still s, okay, which can be obtained by integrating ds over curve c. So your ds now is equal to square root of df dt squared plus dg dt squared plus dh dt squared dt, and integration upper limit for t is tn, which is the value of t at the destination point, and lower limit for t is t naught, which is the the value of t at the initial point. Okay, so if you have a scalar field phi xyz, integrate with respect to integrate over curve c. So you have phi ds over curve c. So now when you see x, you replace it with the parametric equation for x, or the x component, which is ft, and y with the y component, which is gt, and z here is replaced by h, which is the z component, and ds here is df dt squared plus dg dt squared plus dh dt squared square root, and the integration is with respect to t. Okay, so for a vector, for line integral of a scalar field in xyz space, you have no choice. You have to change everything in terms of t. So the arc length is still ds integrate over curve c for both line integral in xy z space or in a xy plane. Okay, how are we doing with time? All right, so for the example, I'm going to save this in our next video. Thank you.